Find a property of f of x. In this problem, a surface is defined by the function f of x, whose value depends on x1 and x2. We need to determine if this surface is positive definite, positive semi-definite, negative definite, or indefinite. The definition of these properties are as follows. A positive definite function is one in which, for any non-zero vector, x transpose hx is strictly greater than 0. In this inequality, h is the second-order partial derivative of the function, often referred to as the Hessian matrix. A positive semi-definite function is defined as one for any non-zero vector of x transpose hx is non-negative. A negative definite function is one in which, for any non-zero vector x transpose hx is strictly negative. And an indefinite function is a surface which is neither positive semi-definite nor negative semi-definite. Returning to our function f of x, we'll first evaluate the Hessian matrix H by first taking the gradient g f of x, which is the first partial derivative of the function with respect to all n variables. Since we only have two variables, x1 and x2, then the gradient is a matrix sized one row and only two columns, and equates to 2 times x1 minus 4, 2 times x2 plus 2. The Hessian matrix of a function f of x is the square matrix of second-order partial derivatives whose size is n by n. Since we're only dealing with two input variables, x1 and x2, the Hessian is a 2 by 2 matrix, which equals 2, 0, 0, 2. Next, we'll evaluate x transpose h of fx, x, to determine the property of the function f of x. In this equation, we'll keep the x vector in its generalized form as x1, x2. And after plugging in the Hessian matrix, this value equates to 2 times x1 squared plus 2 times x2 squared. And for all non-zero real values of x1, x2, this value is strictly positive. When reviewing the possible solutions, the answer is A. Since positive definite functions are a subset of positive semi-definite functions, it is also technically true that f of x is positive semi-definite. However, it's best to answer A since it is a more precise answer. We can also check for positive definiteness of a function by returning to the Hessian matrix hf of x. Then, according to Sylvester's criterion, the function is positive definite if the upper left I by I matrix of the Hessian has a positive determinant for all I ranging from 1 to n. For I equals 1, the determinant is simply the value itself, 2, which is positive. For I equals 2, we'll evaluate the determinant of the entire Hessian matrix since n equals 2, and the determinant equals 4, which is positive as well. Therefore, we confirm the positive definiteness of the function using Sylvester's criterion. Lastly, if we revisit our plot of the function and view a contour plot of the function, we notice the level sets are continually increasing as x1, x2 moves further away from the minimizer x star, which is located at 2, minus 1.